Okay, so welcome back. We continue today with these squares for ways and the closing up. So remember, last time we talked about the introduction to least squares methods. We talked about pseudo inverses and the normal equation, and we kind of introduced the Gram Schmidt method. So I'll give just a few words about the main context again. We are talking about solving linear equations, but these systems are quite unsolvable. So the first method proposed used what we call the pseudo-inverse matrix, which we call A+, and there are different ways to get it. And it satisfies some kind of set of properties. And then we moved on to the projection. And the projection, in fact, solves again a linear system AX equals B, but with the case that B doesn't belong to the column space of A, we do use what we call a projection matrix, capital P, to project B on the plane formed by the column space of A. And we already set some beautiful formulas on how to do that. So at the end of the day, we found out that the approximate solution, which we call the X hat, is similar to the one obtained with this pseudo-inverse method. So then we started talking about the Gram Schmidt method, and the main principle of the Gram Schmidt method is to obtain a kind of factorization we call QR factorization, where the columns in Q are orthogonal. So we say that the Gram Schmidt method orthogonizes the columns of A, and this makes X hat, or the approximate solution to the linear system, quite easy to find. So in fact, this orthogonalization counts a double number of operations to compute as a regular solution, but in fact, the orthogonal vectors, they do usually provide what we call numerical stability. And stability is quite important when we do deal with ATA matrices, which are nearly singular. Okay? So the main steps of the Gram Schmidt method, well, it's mainly based on the fact that that we are going to iterate through the columns of A and form new columns, Q columns, which are orthogonal to each other. So we work on the orthogonal matrix in Q, and we try to form it. How do we proceed? So we take the linearly independent columns A1 to AN of A, and we should end up with orthonormal columns Q1 to Qn. And we do start with the first column, which is Q1, which is A1 divided by A1. And hence here the Q1 its norm is equal to, right? I didn't correct this mistake. So then what we should do is we should use this Q1 to obtain a new, this is a temporary column, in fact, we call capital A2, which uses the second column, the next column to A1 in A, which we call A2. And this is the way to compute capital A2. It's A2 minus A2 transpose times Q1, all times Q1. So you do obtain here a new column, we call it capital A2. In fact, Q2, the new column you're going to have, going to add to the matrix Q, is just A2 divided by A2. Okay, this way, in fact, Q2 is already orthogonal to Q1. And you continue on iterating this way. So, for example, you do form for the next column Q3, you need a temporary vector or column A3. And this is how capital A3, and this is the way it's obtained. It uses the next column in A, which is A3, minus A3 times A3 transpose times Q1. So this way you make sure that capital A3 is orthogonal to Q1, and also it should be orthogonal to Q2. So with this operation, you make capital A3 orthogonal to both Q1 and Q2, and this way, Q3, when you divide A by its norm, you may obtain a new column Q3, which you add up which adds up to the matrix Q. So this is the general formulation. in fact, of the QR factorization. And since we are willing to find something of this form, A equals QR, so with this Gram Schmidt method, you've iterated through the terms of A to obtain Q, but still you didn't find R. Now to find R, since you do satisfy the fact that A equals QR, and what else? Q is orthogonal. If Q is orthogonal, then Qt times Q is equal to I. Right? So in that case, if you multiply both sides by Qt here, again, you multiply both sides of A and QR by Qt, you do obtain R equals to QTA. Okay? And this is then the way to get R. So you end up with R equals QTA. And in fact, Rij is supposed to be our triangular. So this is the formulation, in fact, in terms of columns. These are the columns of A. They were used by the Gram Schmidt method to obtain orthonormal columns Q1 to Q3. And these orthonormal columns, once transposed and multiplied by A, they give you this upper triangle of beautiful matrix R. We call R. And so this guy is just R. Okay? So on the day, what did you have? You had QR equals A. And this satisfies the fact that when AT is multiplied by A, well, you can write it this way. So when producing the transpose again inside the QR factorization, well, here you do see that the identity matrix appear, and you have RT times R, which means that, in fact, what did you do? You really, saved your day. You really lowered the number of operations you need to perform to work on the solution of the linear system. So you end up having this least square solution to AX equals B. You just need now to do what? In fact, instead of solving AX equals B, you can set up X hat to be equal to the formulation you had for A, which is QR, okay? And multiplied by its transpose. So in fact, you get X hat, which is R minus 1, Qt times B. And remember, R minus 1 here is very easy to obtain. It's much less costly than the fact that you need to invert A. And since we are dealing with, we said in this whole chapter, we're dealing with very large matrices, you've really saved your company or your project or your team a lot of computational effort. So if you are using MATLAB, the way to do it is to call the QR function. QR function in MATLAB that works this way. So it returns the Q matrix and the R matrix. And generally said, the Rij's component are QITs multiplied by the AJs. Okay? So because you just had R equals QT, okay? So you do end up with the following formulation. So in this example, for instance, I have A equals 3, 1, 2, 2, 3, 1, 1, 2, 3. And the iterations manually through the Gram Schmidt method yield this one. And the first vector, of course, is very easy to obtain. It's Q1, which is 1/3 times, this should have been 2, 1. Yes, I didn't correct this one again. So it should have been 2 to 1, okay? And you've used it to generate U2. How do you do U2? So we said it's A2 divided by norm of A2, okay? And to obtain this guy, said that A2 itself is A2, small A2, minus open brackets, is A2 times Q1, A2 transpose, so times Q1 times Q1, this way. Okay. So this is the way to perform. So for instance, for this example, this is what MATLAB returns. And you should notice something is that you may not obtain by hand exactly in the same order of columns. Right? So you might not obtain exactly the result, as in fact it works with the column permutation matrix we call P, which inserts P plus before A. So you, in fact, you're trying to exchange the columns of A by order of importance. In fact, the Gram Schmidt file, Gram Schmidt.py, in fact, implements this method. So I'd like to show you here, I'd like to share with you my screen to show, as usual, how we do it with Python. So hopefully it's going to work. So I'm willing here to show you. You see my studio, right?
Yes.
Yes, Rakan, go ahead.
No, sorry, Dr. by mistake.
Okay, bro. So here, for instance, I'm trying to solve what? A 5 by 5 system, which is AX equals B. You see this beautiful matrix A, well, it is, I mean, it's already huge. I mean, solving 5 by 5 system is not something trivial to do by. Okay, and even if you're trying to do it, I mean, trying to invert A, even if A is invertible, this is definitely not something recommended. So, first of all, I'm trying to make sure here that with this iteration or with this command determinant of A, I'm trying to make sure that determinant of A is non-zero. Why am I doing that? Because I'd like to see if the determinant is zero, then, well, there's no way you can solve by matrix inversion. Am I right? Okay. So I'm just going to print it just for curiosity, just to make sure that it's not zero. Okay. And then I'm going to compute the inverse, just calling the inverse function in a linear algebra package. Okay. And what am I going to do? I'm going to just, first of all, find x0, which is the exact solution to the system itself. Okay? Then the intention of this file is to show you that the QR factorization works well. So after that, well, I'm going to say, wait a second, let's try the QR factorization. So I'm going to call what we call the QR function, which exists also with the NumPy package. In fact, in the Miller algebra package, sub-package. So you can call QR, and it's almost exactly the same command in MATLAB, but without brackets, which come before and after Q and R. Okay? So I'm going to print Q and R, and I'm going to do what? I'm going to compute this P, which is equal to, it's kind of transition matrix, which is equal to what? It equals Q times Q transpose times B. Okay? I'm just multiplying Q transpose times B. And finally, I'm multiplying to get X, in fact, the solution. I'm going to multiply R minus 1 by Q transpose B. Okay? And that's the whole day. So at the end of the day, what I need to check is that the X0 I obtained by the hard way, by inverting A, multiplying, is exactly the one I obtained with the QR factorization. Okay? Everything is set. Any question on this, guys? Is it okay? Okay, so let's proceed. So, yes, go ahead, Aziz. Clear. Okay, so let me just run it and see what happens. So, of course, if everything runs well, I mean, we should end up having x0 exactly as x. So remember, we are in debugging mode, so it takes a little bit of time. Let me hide this first. And this should definitely be the same. So let's see what happens. Let's go step by step. So first of all, the determinant of A, as you read here, is 9, which is definitely not 0. So A minus 1 exists. And because I cheated a little bit, so I knew that it would happen, so I didn't put a condition. But if we are working in algorithmic style, everything next should be only happening if the determinant is not 0. So x0 here is what? Is 2 1/3 minus 2.55 2/3 and minus 0.777, so about, I think, 7/9. Okay, so this is the solution, or the exact solution to our linear system. Now, what is displayed after that is the result of the QR factorization. So this is the beautiful matrix Q got, okay, returned by the QR function. And as you see here, you can check that basically they are, well, you can check that it's an orthogonal matrix by multiplying QT by Q to obtain R. But check out, guys, what happens. R is as expected. It's a beautiful upper triangular matrix. This is T, which we said is equal to QTB. QTB. So basically, the system you're solving now is different. You're not solving anymore AX equals to B. You're solving a different system, which is this guy we said is QB, right? QTB, sorry, QTB. So basically, you're solving a system on the R matrix. And if I multiply this B by R minus 1, before you can end up having this solution, which is exactly the solution we had before, as you see. It's 2, 1/3, minus 255, 0.666, minus 0.777, which is exactly the same solution. Okay? So things are behaving quite well. You got it, guys? Okay. So you can, if you, for your curiosity, you can check that QTQ is equal to I. So this is for. So I will upload this file later on, and that was for curiosity to see how things happen with Python if I wanted to do it by hand and not, let's say, do it the dumb way with MATLAB. Okay? So I'll start this right now. If I'm able to move my mouse, yeah. Okay, so now I'll go back to my slides. So I was sharing these files, okay, and here we go again. So that was the last slide we've seen. Now I added to this 2 new slides, which talks about another way to do this, which we may call it here the fourth way. The fourth way. And the fourth way here uses what we call the householder reflection matrix. What is the reflection matrix? Well, it simplifies, in fact, it makes the computation of the columns in the Gram Schmidt method more precise. So this is the main principle. We will not dive deeply into the details. We'll just use the formula as it is and apply it on examples. Okay. So the computed Q here with the Gram Schmidt method, in fact, won't be exactly orthogonal from numerical stability point of view. It's just hard. Okay. So if you're having huge matrices, this numerical stability becomes quite an important concern. So the good way to create an exactly orthogonal Q, in fact, would be to do what? To do it the householder way. Okay? He did it defining a new matrix we call the H matrix, householders matrix or reflection matrix, which is defined this way. It uses the identity matrix minus 2 times, well, VVT over length of P or normal V squared. Okay? And we will see that U could be used as an arbitrary vector. So the particular thing about this U is, in fact, it's a unit vector from another vector which is called V. So it's just V divided by its norm. Okay. So in fact, if you multiply U by its transpose, you get VVT all divided by V squared. So basically, this is just explaining why UUT is just taking the place of VVT divided by the normal V squared. Okay, so basically you're saying that H is equal to I minus 2 times U UT transpose. Okay, so what is particular to this householders matrix? It is symmetric and orthogonal. So you can check it with this formulation, if you multiply H by transpose, you always get R. So what are we going to do? We're going to use it such that at every step, we do generate a new matrix. We call HI, so at step I, for example, you use 2 or 3 times, you have H3, H2, H1 times. Okay? At the end of the day, if you compute n-1 steps, okay, like, in fact, it is quite similar to what the Arnoldi iterations does. So at the end of the day, this product, Hn-1 times all matrices till you reach H1, it takes the place of Qt, but more than that, it is more precise. Yes, Abdulaziz.
So what's U and V?
Sorry?
What is U and V?
We said that U is an arbitrary unit vector. So V is an arbitrary vector, and U is just the unit vector obtained from V. We will see it with the next example. Okay, so this way we get, in fact, Q is replaced by the product of all these matrices. So hold on a second. So this is the example that illustrates how things work. For example, here in this case, I'm willing to solve the system. It's quite simple, so we can use it by hand. We can solve it by hand. So this is AX equals B, and this is this is A for 1, 3, 2. And B transpose, so basically what I'm trying to solve is this use 1, 2. Okay? So basically I'm saying that 4x1 plus x2 equals 1, and 3x1 plus 2x2 equals how much? Equals 2. Yeah. So this is my system. So in this case, we have chosen 2 vectors. A, which is the first, we have the first column as you see in A. Okay, and another vector that has the same length as A, which we call it R. Okay. The good way to create an exactly orthogonal matrix Q is to build it the way Householder did. So the way Householder did is, in fact, about these vectors, how to construct them. So what he did is that he used A minus R to form, first of all, V. Okay? So once he picked for 3, there are many ways to form a new column here, R, and basically here in this case, it's simple. Okay? So it's 5, 0, and as you see, in that case, the condition is that the 2 norms are equal. So if V is equal to A minus R, so it's minus 1, 3. So just subtracted R from V, he got minus 1, 3, which means that his U is in fact minus 1, 3 divided by the number of U, which is root of 10. Okay? That's why I said here the choice of V is an arbitrary choice, because the choice of R is just arbitrary, as you can see. The only condition is that it has to satisfy the fact that the norm of A is equal to R. Okay, so once you obtain U, now all you have to do is just to apply the formula that gives you the first matrix H1. In fact, this H1, but you stop here because now the n-1 dimension is just 1. So you have only to do it once. So if you compute H1, which is I minus 2 ut, it just gives you 1 over 5, 4, 3, 3 minus 4, which ends up to be your new Qt. So you can see that, for instance, if you multiply this matrix H by A, which is 4, 1, 3, 2, you get exactly this matrix. And particularly, you can see that now you have an upper triangle matrix. Okay? So basically, it's just R, as we did before with the Gram Schmidt method, with the QR factorization. So since you have X now to solve, basically it means what? It's telling you that S5 X2 is equal to what was the to QTB. Okay? Remember, we changed the vector, now it's QTB. So it's 7 multiply Q by B here, you get the two right-hand sides now are 7 minus 1. Here I choose to write in line to subspace. So basically, it means that you have the solution for your problem, and here it ends up to be 1, 1. Okay. Got it, guys? So this is the solution for our system. This is the way householder did. Okay, and it's a way more beautiful way to do it. Okay? So you save a lot of computational effort if you do the householders. So basically, this is the last part in 2.2 I wanted to have. Any question on this, guys? Yes, Khalid.
Doctor, why did you choose 4 and 3 for it? Why did you choose 1?
Okay, because what I understand here is that I need the maximum. Let me go back. The maximum dimension I'm going to reach is n minus 1. See here? So I can only work on the first column, which is A1. So basically, I will not have to do this because of the reduced dimension of my problem. So I will work just with A1. I would be able to get, with one step, one single multiplication, H1A, I'll be able to get an upper triangular matrix R, just because of the reduced size. Okay. Now, if we had to do it the second way, I will have to pick up A2 to define new matrix H. Okay. So this way we can solve using the householder's reflection matrix. Any other question, guys? Okay. So hopefully we'll see some other examples which we may illustrate this in a more perfect way, and there are some we can work on it. So so this is for the first part for today.